Pressure relief and depressurization. Overview of pressure relief philosophy and process safety. Pressure relief and depressurization systems form a critical part of the layered safety strategy in process facilities. They act as the final safeguard against overpressure scenarios that could result in equipment failure, fire escalation, environmental release, or harm to personnel. These systems must be reliable, deterministic, and effective across all process conditions, including startup, shutdown, maintenance bypass, and fault events. Pressure relief systems typically include relief valves, rupture discs, and thermal expansion relief valves, all designed to automatically relieve excess pressure when process deviations occur. Emergency depressurization systems, by contrast, rapidly reduce system pressure in defined fire or leak scenarios to prevent structural failure and minimize escalation risk. Relief system requirements and failure modes. Relief protection must address all credible causes of overpressure, including blocked outlets, utility failures, reaction runaways, fire exposure, and valve or control failure. Each relief device must be evaluated for these initiating events using standardized calculation methods. Worst-case scenarios, such as 100% vapor breakthrough or full bypass valve failure, must be considered to size relief capacity adequately. Relief systems must remain operable without obstruction due to solidification, valve misoperation, or internal damage. For high pressure to low pressure interfaces, the maximum possible inflow via both control and bypass valves must be accounted for. If both valves could theoretically fail open, the relief system must ensure the downstream pressure does not exceed the hydrotest pressure of the system. Fire case considerations. Pressure relief for fire exposure is mandatory when equipment is located in fire-prone zones and contains potentially blocked-in liquid. Exceptions apply only to small volumes of high-boiling, non-toxic liquids. Relief design must assume cessation of all internal and external flows post-fire detection, with equipment exposed to flames up to 8 meters in height. Relief sizing in fire scenarios is based on heat input to wetted surfaces and requires inclusion of vessel internals and connected piping. Active fire protection, e.g. water deluge, cannot be credited unless robust passive protection, such as fire-proof insulation, is independently verified. Instrumented protective functions in relief strategy. In certain cases, it may be desirable to supplement or reduce reliance on mechanical relief systems using high-integrity instrumented protective functions, IPFs. These may be applied where flaring is environmentally prohibitive, relief systems become prohibitively large, or where rapid isolation offers significant benefit. Examples include well manifolds, where overpressure protection is achieved by fast-acting valves based on high-pressure detection. Relief valve sizing may be adjusted based on validated reliability studies. Cooling failure scenarios, where common mode failures across multiple columns can be mitigated using high-pressure shutdown IPFs to limit aggregate flare loading. Air-assisted relief valves, where pneumatic actuators reduce the margin between maximum operating pressure and set pressure, providing both operational flexibility and cost savings. Complete substitution of relief valves with IPFs is rare and requires regulatory approval. Even where IPFs are used, mechanical relief must generally remain for individual unit protection. Relief device selection and design integrity. Relief valves must be selected based on expected service conditions, including the phase of the relieving fluid, gas, liquid, or two-phase, expected back pressure, and susceptibility to corrosion, fouling, or freezing. Device types include spring-loaded, balanced or unbalanced, pilot-operated, air-assisted, bursting discs. Each type has specific criteria for application. For example, balanced bellows valves are used where back pressure exceeds 10% of set pressure. Pilot-operated valves are favored for clean surfaces with high back pressure tolerance and minimal leakage. Bursting discs are considered for rapid response or highly corrosive duties, but require replacement after actuation. Relief valves cannot effectively depressurize systems under fire. Dedicated depressurization systems must be designed to reduce pressure to 50% of design within 15 minutes under fire exposure. These systems must consider initial internal pressures and fluid inventories, heat input from fire, effects of vaporization and expansion. Remote operation must be available, typically from the control room, with automatic activation in unmanned facilities. Depressuring should be sectionalized to reduce flare loads, and flare headers must be designed to handle peak and cumulative depressuring events without overpressure. Relief system layout and accessibility. Relief valves should be located close to the source of overpressure, typically at the vapor space of equipment. Pressure drop between equipment and valve inlet must not exceed 3% of set pressure. Installations must allow for safe drainage, venting, and maintenance access. Inlet-outlet piping must avoid low points and accommodate freezing or high-temperature risks with proper tracing or insulation. For systems with multiple valves or staggered operation, careful tagging, venting provisions, and mechanical locking systems are essential to prevent accidental isolation. Flare system Flare systems must safely collect and dispose of relief gases during normal, upset, or emergency scenarios. Key design considerations include sizing based on dynamic load analysis, segregated headers to prevent incompatible mixing or hydrate formation, knockout drums for liquid separation, heat radiation and dispersion control, acoustic vibration mitigation, continuous purge and ignition assurance. Designs must meet limits on noise, thermal radiation, and toxic dispersion. Systems handling sour or oxygenated gases may require separate stacks or dedicated treatments to prevent corrosion and ensure safe combustion. Conclusion: systematic, layered protection. Effective pressure relief and depressurization require a systems-level approach that considers hardware integrity, functional performance, diagnostic coverage, and regulatory compliance. When properly designed, installed, and maintained, these systems form the backbone of plant safety, enabling safe containment and controlled response even during extreme process upsets. Fire case requirements. Protection against overpressure due to fire is a core requirement for all process equipment exposed to credible fire scenarios. Relief devices must be designed to vent vaporized contents resulting from heat input to the wetted surfaces of process vessels during fire exposure. Fire relief must be considered when the equipment is located where a sustained, intense fire could occur. It is possible the equipment could remain blocked in, i.e., without active inlet-outlet flow when a fire happens. Exceptions may be made for small volume equipment, typically 500 liters, that contains non-toxic liquids with boiling points above ambient temperature, provided the risk of fire-induced overpressure is negligible. Key design assumptions for fire cases include: all inflows/outflows to the affected equipment stop shortly after fire detection and operator intervention. Internal heat sources cease upon shutdown. Emergency shutdown (ESD) valves are assumed to isolate streams early. The fire zone is assumed to be 300 metasquarters in typical processing facilities, and the vertical flame height considered is 8 meters from grade or from any platform where liquid can pool and sustain combustion. Relief device sharing. If the equipment already has a relief valve adequately sized for non-fire scenarios, that valve may also serve the fire case, provided it meets the sizing requirements for both situations. Otherwise, additional or larger valves may be needed. Relief rate calculation for fire exposure. Relief loads must be calculated based on the total heat absorbed by the vessel's wetted surface. Relief sizing must consider liquid vaporization, expansion, and vapor density changes. The assumed liquid level should include typical operating levels plus any liquid draining from internals during heating. Fireproofing considerations. No credit may be taken for active fire protection, such as deluge systems or fire response, in sizing unless passive fire protection, e.g. certified fireproof insulation, is present and verified. Fire-resistant insulation must withstand fire heat and water jet impact if it's to be credited with reducing required relief loads. Piping considerations. Process or utility piping typically does not require fire relief-specific relief valves, except where thermal expansion could cause dangerous pressure buildup in blocked-in liquid sections. Design should aim to eliminate isolated liquid-filled sections vulnerable to fire exposure. Fire areas and documentation. All fire zones must be identified and clearly marked on the plant plot plan. Each relief valve datasheet should include the fire area number relevant to its design basis. By applying these principles, the pressure relief system ensures containment integrity during fire events, even when primary containment systems are compromised. Plate and printed circuit heat exchanger relief requirements. When protecting plate type or printed circuit heat exchangers against overpressure, the same principles applied to shell and tube exchangers must be observed. While these modern compact exchangers often feature matched design pressures on both sides, the risk lies in downstream equipment that may be rated for lower pressure than the exchanger itself. Key considerations include pressure differential scenarios. Overpressure can occur if the high pressure side of the exchanger ruptures or leaks into the low pressure side. The relief system must be designed to protect not just the exchanger, but also any connected low pressure vessels or piping that could be exposed to unintended high pressure. Worst case failure assumption. Relief sizing must be based on a full longitudinal rupture along a single corrugation channel in the exchanger plate pack. This assumption represents the maximum credible breach path and results in a conservative relief flow rate. Relief flow estimation method. Identify the maximum number of inlet ports or channels that could feed into the ruptured path. Calculate the total potential inflow area by summing twice the cross-sectional area of each of those inlets, accounting for simultaneous flow from both sides of the breach. Design implication. This method ensures that the downstream system is protected against the highest possible inflow resulting from a catastrophic failure, aligning with the principle of conservative design for overpressure protection. In all such cases, relief device selection and sizing must be verified against the resulting worst-case flow, and the relief path must be free from restrictions or back pressure that could impair valve performance. TAT, thermal expansion relief valves, TERVs. Thermal expansion relief valves are essential safeguards in liquid-full systems that be inadvertently isolated while exposed to heat sources, such as ambient temperatures or heat tracing. Even small temperature increases can cause sharp pressure rises in incompressible fluids, posing serious risk to piping and equipment integrity. Key design considerations include thermal expansion behavior. A fully liquid-filled system can experience theoretical pressure increases of 5 to 15 bar per degree Celsius temperature rise. While perfect isolation and compression are rare in practice due to minor system leakages, these theoretical values justify conservative design assumptions. Situations where TERVs are usually not required. Process piping that is continuously in operation and unlikely to be blocked in. Systems that are not more than 95% full of liquid. Fluids that are non-toxic, non-corrosive, and have boiling points above ambient temperature. Systems with engineered weak points, e.g. flanges that relieve minor overpressures safely. Typical applications where TERVs are required. The cold side of heat exchangers that can be isolated. Piping containing 2,500 liters of LPG or toxic liquids that may be blocked in during operation. Cryogenic lines or subambient piping that can be isolated, TERVs required regardless of routine isolation frequency. Blocked-in piping in outdoor or solar-heated areas with significant heat gain potential. Design and sizing guidance. Use a minimum orifice area of 0.71 centimeters square meters, typically 25 by 25 millimeter valves. Set pressure may be up to 110% of maximum allowable working pressure, MAWP, if isolation procedures include pre-drainage to reduce fill volume. Select materials suitable for process fluid, temperature, and corrosivity. Bronze valves may be used for water service with threaded ends. Operational considerations. TERVs should be located as close as practical to the protected volume. Discharge piping must be kept free of ice or debris buildup. Procedures should include draining small volumes after block-in to further reduce risk and avoid nuisance valve actuation. TERVs are simple but crucial elements of pressure protection. Their correct application prevents avoidable system failures caused by trapped liquid thermal expansion, particularly in systems where operational isolation is common or inevitable. TASH, use of instrumented protective functions, IPFs, in pressure relief strategy. Traditional overpressure protection employs two independent layers, a primary pressure control system and a secondary mechanical relief device, such as a relief valve. This dual-layer design ensures that if control fails, pressure can still be relieved safely. However, in some applications, reliance on mechanical relief may be technically or economically burdensome or environmentally undesirable. In such cases, instrumented protective functions, IPFs, may be used to complement or reduce the size and impact of relief systems. Key principles of IPF integration: primary function. An IPF monitors a process variable, typically pressure, and automatically initiates a protective action, such as shutting a valve, stopping a compressor, or isolating a well to prevent overpressure from occurring. Substitution limitations. Relief valves cannot be fully replaced by IPFs unless relief devices are physically impossible or impractical to install. Even then, regulatory authority approval is typically required. Failure tolerance. IPFs must be independently verifiable, fail-safe, and evaluated for common cause failures. Where multiple IPFs exist in parallel systems, assumptions must be made about potential concurrent failures. Typical applications of IPFs in pressure relief: A. Overpressure protection in multi-well systems. In systems where equipment is exposed to the shut-in pressure of multiple wells, often exceeding the equipment's design pressure, using conventional relief sizing to accommodate full well flow may require unrealistically large relief capacity. Instead, fast-acting valves triggered by high-pressure sensors can be used to shut off upstream wells. A reliability study must determine the number of wells the relief valve should be sized for, e.g., if the IPF fails to isolate some, the probability and impact of common mode failures, ensuring that not all wells can remain open simultaneously. B. Reducing flare loading during common mode failures. Loss of a cooling medium, e.g., cooling water or air cooler fans, can disable heat rejection systems on multiple distillation columns, triggering simultaneous overpressure across several systems. Without mitigation, this would require extremely large common flare headers and tips. High-pressure triggers can be used to shut off heat input, e.g., closing reboiler feed or fuel supply on each affected column individually. Design must assume at least one IPF may fail. The common relief system must be sized to handle the largest individual relief load from such a failure. If there are more than 5 IPFs, assume 2 may fail and size for the 2 largest concurrent relief loads. C. Application of air-assisted relief valves. These are spring-loaded relief valves fitted with a pneumatic actuator. The actuator maintains a tighter seal close to the set pressure, allows for a smaller margin between maximum operating pressure and set pressure, typically 5% instead of 10%. In the event of an instrumentation failure, the valve will still open at no more than 110% of its set pressure due to a small secondary relief valve ensuring mechanical redundancy. A 1002 1 out of 2 voting system is recommended to maintain the reliability of the IPF portion. Design and approval requirements. Detailed engineering validation is required for any application of IPFs in place of or alongside relief devices. Systems must undergo hazard and risk analysis, failure mode evaluation, and logic validation. All IPFs must be submitted for owner-operator approval and, in many jurisdictions, also for regulatory review. IPFs must not share sensors, power supplies, or logic solvers with the Basic Process Control System, BPCS, unless failure independence can be clearly demonstrated. By integrating IPFs correctly, designers can reduce flare size, minimize environmental emissions, and maintain compliance without compromising protection. However, they must be engineered with the same rigor as any safety-critical system, acknowledging the complexity and risks introduced by reliance on instrumentation.